In this video, we're going to be looking at conditional probability, independent and dependent events in the multiplication rule for probability for two or more events. So conditional probability occurs. It's the probability of an event occurring given that another event has already occurred. The conditional probability of event B occurring given that A has already occurred is denoted by the probability of B given A. Finding conditional probabilities. So 2 cards are selected in a sequence from a standard deck of 52 playing cards. Find the probability that the second card is a queen, given that the first card is a king and was not replaced. So because the king was not replaced, our sample space will change. So the sample space changes not replaced. So without replacement, that's going to change our sample space. So now instead of having 52 cards, I have 51 cards. And there are 4 queens in the deck, so we're going to have 4 out of my new sample space of 51. And when I multiply that out, I'm going to get 0.078. Every time we're going to give a probability, I'd like the fraction and then 3 digits. Okay, there are a couple exceptions, but by and large, that's what we're going to be doing. So back to our definition of conditional probability. So given that another event already occurs, so this changes our sample space. So I'm going to write that up here. So the sample space changes. Sample space changes. And I'm going to circle that given that, okay, because that is what tells us that the sample space has changed. So now we're going to look at something called a two-way table. So for number 2 through 5, the table below shows the results of a study in which researchers examined a child's IQ in the presence of a specific gene in the child. So we have a high IQ, normal IQ, gene, and not gene, and there were 102 people surveyed. Find the probability that a child has the gene. So the gene present is 72, and the total is 102. So 72 divided by 102 will be 0.706. You can check that with your calculator if you want. Number 3, the probability that a child has a high IQ given that the child has the gene. So given that the child has the gene is present, that total pertains to the 72. So our sample space changes. Okay, so now our total is 72. And we want to find the probability that the child has a high IQ. Well, that's going to be this 33. So I'm looking at this particular column right here for this one. Okay, so I have 33 out of 72. And when I do that out, I'm going to get 0.458. Okay, then we can look a little bit at something called a complement. Find the probability that the child does not have the gene. Well, 72 kids have the gene. 30 do not, for a total of 102. So not having the gene would be 102 minus 72 to get the 30. So you can just do 30 over 102. Okay, and that comes out to 0.294. And incidentally, I could have taken number 2 and I could have done 1 minus number 2. So 1 minus 0.706. And let's check that out. 1 minus 0.706. And guess what? I get the same thing because these are the complements of one another. So this is a complement. Complement is when 2 things add up to a probability of 100%, or in this case, 1. So I'm treating 1 as 100. All right, finally, So we looked at the not gene present, we looked at the total gene present, and then we looked at a given that question, which is conditional probability and changing our sample space. So now we're going to do one more question with this two-way table. Find the probability that a child does not have the gene given that the child has a normal IQ. So we're going to look at given that a normal IQ. So here is a normal IQ total. Okay, and does not have the gene. So now we're looking at this piece here. So again, the sample space changed. All right, so our sample space changed. Okay, and we have a total of 50 children with a normal IQ. So given that a child has a normal IQ, we want to say how many do not have the gene. So that's going to be 11 out of 50. Okay, you can grab a calculator if you want and get 0.22. We think that rounds exactly. Okay, so you don't need to put an extra 2 or anything. So it's just, or 0. You can just leave it as 0.22. All right, we call these a two-way table because we read them two different ways. So on the top, the gene was present, yes or no. And then on the left, we had the IQ, normal IQ or a high IQ. All right, so that's an introduction to conditional probability. The second page of our notes packet talks about independent versus dependent events. Two events are independent when the occurrence of one of the events does not affect the probability of the occurrence of the other event. So independent means the events do not affect the other. Two events, A and B, are independent when the probability of B given A equals the probability of B, or when the probability of A given B equals the probability of A. If events are not independent, they are dependent events. All right, so this sounds kind of complicated, but it's not that bad once you understand. Examples of independent events are rolling a die and tossing a coin. These are probabilities with replacement. This I'd probably try to memorize. And then examples of dependent events are probabilities without replacement. So these are kind of huge concepts up here. Basically, if one thing affects the other, if one thing has an effect on the other, it's dependent. Okay, so we're going to classify events as independent or dependent. So for number 6 through 10, determine whether the events are independent or dependent. Number 6, selecting a king, which is event A, from a standard deck of 52 playing cards, not replacing it, and then selecting a queen from the deck. So event B is the queen, and since we did not replace it, the sample space changes. I'm going to write SS for sample space, so now this is going to be dependent. Number 7, tossing a coin and getting a head, and then rolling a 6-sided die and obtaining a 6, event B. So A is getting a head and B is getting a 6. Well, guess what? The head, the coin and the die have nothing to do with one another. They don't affect each other in any way, so these are independent events, which is a lot different than number 8. In number 8, you're driving over 85 miles per hour, which is event A, and then getting into a car accident, which is event B. Well, clearly speeding is going to have a higher risk as to getting into a car accident, so this is going to be a dependent example. Same thing for number 9, smoking a pack of cigarettes per day, event A, and then developing emphysema, a chronic lung disease, event B. Of course, the cigarette smoking is going to affect your lungs, so this is dependent. Juul smoking also does that. All right, and number 10, tossing a coin and getting a head, and then tossing a coin again and getting a tail. Well, each time you toss a coin does not affect the other, so these are actually independent. Okay, so just to summarize, independent events was when one does not affect the other, and it's always with replacement. However, dependent events is when one event affects the others, and it's always without replacement. Okay, and that's what we have highlighted up here, so I would try to memorize that or use that as a reference. All right, the last thing I promised you in this video was the multiplication rule for the proper probability of A and B. The probability of two events A and B will occur in sequence is the probability of A and B, so that's the probability of A times the probability of B given that A already has occurred. And we're going to talk about that, and I know the formulas seem a little scary, but once you get this idea of it, it's not too bad. In events A and B, I think that's supposed to be if events A and B are independent, then the rule can be simplified to the probability of A and B equals the probability of A times the probability of B. This simplified form can be extended to any number of independent events, a spinner, rolling a die, anything that won't affect the other. So the big thing here is that you have at least two events happening. So this is multiple events. Multiple events. So that is important to look for. So for number 11, we're going to use our multiplication rule. Number 11, two cards are selected without replacing the first card. From a standard deck of 52 playing cards, find the probability of selecting a king and then selecting a queen. All right, there are 4 kings in a deck. So it's the first probability is 4 out of 32. So the probability of selecting a king is 4 out of 52. You do not put that card back in the deck, which means your sample space changes to 51. So this is dependent. Okay, now the number of queens have not been affected. So you're going to have 4 out of 51. When you multiply that out, the numerator is 16. 4 times 4 is 16. And then 52 times 51 will give you 2,652. Okay, and then we can do 16 divided by our answer, or the 2,652 is a lot to say. We're going to do 3 decimal places, so it's 0.006. All right, you're doing great. We have a few more left on this page, and then we'll be done with our multiplication rule. Number 12, a coin is tossed and a die is rolled. These do not affect each other, so these are independent events. You know that right from the get-go because a coin is a coin, a die is a die. So what is the probability of tossing a head and then rolling a die? Well, a coin has 2 sides, so probability of a head is 1/2. This is classical or theoretical probability. And then rolling a 6, well, that is 1 out of 6 sides of a standard die, so it's going to be 1 out of 12, which is 0.083. So as a fraction, you'd have 1/12. As a decimal, 0.083. All right, the next one. The probability that a salmon swims successfully through a dam is 0.85. Find the probability that the 2 salmon swim successfully through the dam. We have 2 salmon swimming, and we're looking kind of globally here. So this is going to be independent. We have to assume that there are thousands and thousands of salmon going through, at least hundreds and hundreds. And so we're going to say that these events are independent of one another. So you would do 0.85 and 0.85. So that's going to be 0.85 squared. And when you do that out, you're going to get 0.723. Okay, so one salmon swimming through doesn't affect the other one. Okay, now if you look at the next question, 2 cards are selected from a standard deck of 52 playing cards without replacement. Whenever you do not replace, that's going to be dependent. Find the probability they are both hearts. All right, so there are 13 hearts in a deck of cards. And then this one, not only does the sample space change from 52 to 51, but we're looking at another heart. So originally you had 12 hearts, now you only have 12 hearts. Okay, when you do that out, you're going to get 13 times 12. That'll give you the 156 for your numerator. And then I just did the 52 times 51, so I'm not going to repeat that calculation. I got 2,652. And then I can do that quotient, that division, and I get 0.059. So remember, if the next digit is a 5 or more, that's going to bump up to a 9. All right. Number 15. For anterior cruciate ligament, the ACL, reconstructive surgery, the probability that the surgery is successful is 0.95. Find the probability that 3 ACL surgeries are successful. Well, the first one would be 0.95, second one would be 0.95, next one would be 0.95. So these are all going to be independent. Okay, so you're just going to do 0.95 to the third power, which is 0.857. We're also going to look at something called the complement. So find the probability that none of the 3 are successful. Well, if 95% of the time you have a successful ACL surgery, that means 5% of the time you don't. So you're going to do 1 minus 0.95, and that's going to be 0.05. So that's the probability of not successful. Not successful. Okay, but we have 3 that are not successful. So that's going to be 0.05 to the third power. And when we multiply that out, I'm going to include the zeros here just because otherwise your probability would be 0.000 and it's not specific enough. So I do want to kind of go out 3 digits after the zeros. So this is using my complement. When you use that concept of 1 minus the probability, that's called the complement. All right, last question. The probability of a particular rotator cuff surgery being successful is 0.9. Go ahead and try A and B. You can pause the video if you'd like. Letter A, find the probability that 3 rotator cuff surgeries are successful. You're going to do 0.9 to the third power, which is 0.729, and then find the probability that none are successful. Well, that's going to be 1 minus 0.9, which is 0.1. So 0.1 to the third power is going to be 0.001. So in today's video, we looked at conditional probability, independent versus dependent events, and the multiplication rule. Thanks for watching.